Hello everyone, we present to you our work titled RASP, Revisiting 3D Anamorphic Art for Shadow-Guided Packing of Irregular Objects. Sometimes the simple task of packing objects into a container can become a complex puzzle. While simple cuboidal objects can easily be stacked, the difficulty arises when the objects are weirdly complicated, such as parts of a 3D model. Shadow art and 3D anamorphic art have captivated the human imagination for centuries. Drawing insights from these art pieces, the question arises as to can we use shadows or silhouettes to address the 3D packing and part assembly? The answer certainly is yes. Given a set of objects and a container, we know that a fully packed container would appear as a square on two opposite faces and a rectangle on the other faces. The idea is to use this projection information and update the orientations and positions of the 3D objects to cater to these projections, with maximal occupancy and minimal inter-object spacing. This is what we call shadow-guided 3D packing. The problem statement, however, has a dual interpretation. If the elements to be arranged are whole 3D objects, this approach addresses the irregular object packing problem. However, if these elements are parts of another object altogether, it naturally extends to the part assembly problem. The classical approaches produce high-quality results but struggle dealing with large number of objects that often require significant amount of processing time. The closest to our setting is the work by Ma et al. That uses a multi-stage framework and involves object swapping, enlargement, and replacement to reduce the gaps. Zhao et al. Divide the objects into convex shapes for efficient collision detection in physical simulation and pack the objects in an online manner. Consider a set S of n objects, with each object being represented by a triangular mesh. From the shadow's perspective, we assume the light to be collocated with the camera. Hence, finding the arrangement of objects is equivalent to finding the rigid transformation of each object in the set S, such that the rendered image of the learned arrangement is close to the desired target under perspective projection. We penalize the arrangements based on three types of losses: the rendering loss, the intersection loss, and the container extrusion loss. For identifying mesh intersections, unlike the traditional methods which are either heavy in terms of compute or prone to false positives, we propose an SDF-based intersection detection. We pre-compute the SDF of each mesh at a fixed set of query points within a bounding volume. Finding the intersections is now simply counting the points for which the SDF values are less than 0 with respect to more than one objects in volume V. We do not need to compute SDFs in every iteration. We warp the previous SDF to the new SDF through a linear transformation of the learned rotation and translations. Coming to the losses used in RASP, the first is the silhouette loss, which is simply the mean squared error between the target and the rendered image. The second is the intersection loss. For every point in the container, we define degree of intersection, DIS, as the sum of negative of SDFs of the objects that contain the point P within them at every optimization step. Here, DIS of P greater than 1 indicates that there's an intersection of at least two objects at that point, and DIS of P equals 0 represents that the point P is not inside any object. The intersection loss is simply then the sum of degree of intersection at all the query points. The third and the final loss is the container extrusion loss, which is to prevent the objects from being suddenly extruding out of the container boundary. Let Vi be the set of vertices of the triangular mesh corresponding to the object OI, and SC be the SDF of the container C. Here epsilon is the distance between the vertex and the container's boundary that creates a buffer zone around the container boundary to control when the extrusion loss begins to be active. The total loss, therefore, is the combination of all three losses, and the effect of each loss on RASP can be well understood from the figure here. Coming to the result, we compare RASP with Zhao et al. Against 3D packing problem on the IRBPP dataset. Here are a few more results on object packing. Here's another set of results on 3D part assembly on the Fantastic Breaks dataset achieved through RASP. Finally, we present artistic illustrations of multi-view anamorphic art achieving meaningful expressions from multiple viewpoints within a single ensemble. Here are the key contributions of the proposed work. Thank you.